Okay, so welcome to Math 349, Operations of Order. So this is lecture 32, and what I want to do is I want to finish off the discussion on gaps. For those of you who are here in person, you're welcome to grab candy whenever you want. For those of you who are here virtually, you can see how good Amazon Prime is or something like that. All right, so one of the nice things about having things saved on slides is it makes it very easy to say, let's go back to what we did a few classes ago. Just reset us to where we're. So we were talking about looking at integers in the interval, say 2 to the n, 2 to the n plus 1. We're writing them in binary, so all the digits are either ones or zeros. So 1 means we have it, a 0 means we don't. So if we're in the interval from 2 to the n to 2 to the n plus 1, I have to have 2 to the n as one of my sums. So that's why we know we have to start off with m equals 2 to the n. And then after that, for all the other powers of 2, we either have them or we don't. And if epsilon j equals 1, we have 2 to the j. If it doesn't, if it equals 0, then we don't have it. It's possible to have very few gaps. I could have the number 2 to the n plus 2 to the n minus 1, which would only have one gap. If I gave you the number 2 to the n, there would actually be 0 gaps. And then we just want to look at how many gaps do we have of a given length. And the way we measure gaps is how many indices are there between an index that we have and the next index that we have. So if we have index 4 and index 9 and nothing in between, we would have a gap of length 5. And so we drew a little picture to talk about how it was. So if we want a gap of length g starting at I, we have to have 2 to the I plus g, nothing in between. And that's what all the x's are denoting. And then we looked at which stuff were free and which stuff were not free. So if it was free, we would have two choices. We either have a 0 or 1. And then we just multiply all of the free spots together. And this gave us the number of times we had a gap of length g starting at I and ending at I plus g. And of course, there were some restrictions on I. I couldn't be too large or I plus g would go past n. And so we got a beautiful formula at the end of the day that the number of choices was equal to 2 to the negative g times 2 to the n minus 1. And 2 to the n minus 1 is very nice in terms of just how many elements do we have in this interval. It's a nice relation to the total number of elements. Okay, so now if we want to calculate how many gaps do we have of length g when we look at all possible numbers between 2 to the n and 2 to the n plus 1, we don't care where the gap of length g is. So a given number m could have multiple instances where it's giving you a gap of a fixed length g. And that's why we introduced these wonderful variables x, I, g, n. And then again, notation matters. So when I look at this, the I tells me where do I start, the g tells me how big of a gap it is, and the n tells me where I live. I live from 2 to the n to 2 to the n plus 1. And so this is the number of integers with a gap of length g starting at I. And so if we sum this over all possible values of I, that will give us the total number of gaps of length g. And we got 2 to the negative g, 2 to the n minus 1, n minus g plus 1. All right, so now if we want to calculate the percent of gaps of length g, we just need to know one more piece of information. This is how many gaps there are of length g. What would we need to know to get the percent of gaps of length g? Total gaps. And how would you get the total gaps? So I need to know how many total gaps are there among all the decompositions. I know how many gaps there are of length g. So yeah, it's sum of all, well, sorry. That's one way I can do it. So one way I can do the problem is I can sum over all values of g. So we're just reviewing what we were doing before. So we can sum over all values of g. And so when we look at this, some parts are going to be easy to sum, some parts are going to be hard. The n plus 1 times 2 to the negative and 2 to the n minus 1, that's just a fixed constant when n is fixed. The 2 to the negative g, that's just a geometric series. Oh, we can do that without too much trouble. The fact that we have, unfortunately, a g here, it's now going to be the terms of a geometric series but times something. Well, it turns out there's a beautiful technique called differentiating identities, which allows us to handle stuff like this. So again, to get the total number of gaps, we just sum over all the gaps. There are two pieces, as I remarked. The first piece is very easy. It's a finite geometric sum. The second piece is almost a geometric series. We have these extra factors of g. Now we're going to be interested in what happens as n goes off to infinity. Now, as n goes off to infinity, 2 to the n minus 1 is going to explode, but that's okay because the number of gaps of length g was being multiplied by a factor of 2 to the n minus 1. So that's okay. They're going to cancel each other out. Now, these sums only go up to n minus 1, but if we let these sums go further, it really wouldn't matter once n is large. Think of n as a trillion. 1 over 2 to the negative trillion is really small. And if we summed the entire tail from there to infinity, it would be such a negligible change that you could say, well, rather than writing down what the exact answer is, if we just let the sum go off to infinity, it's really not going to change anything. And so we might as well just do that to make the analysis a little bit easier. How many people still balance their checkbooks or their savings accounts? You check your credit card statements all the time. If you're within a few pennies, do you care? No. And so if it's a really small error, it's often not going to matter in the limit because we're going to look at what's going on as n goes to infinity. So we really only care about the main term. So the two pieces to analyze, the first was the 2 to the negative g, 2 to the n minus 1, n plus 1. Well, we can pull out everything but the 2 to the negative g, that's 1/2 to the g. And we can sum this using the geometric series. We'll use the geometric series formula. If we use the finite formula, we're going to have this correction. It's going to be 1 minus 1/2 to the n. Well, if n is a trillion, the difference between 1 and 1/2 to the trillion is so small, just drop the 1/2 to the trillion. And so the first piece is essentially 2 to the n times n plus 1. Okay, and we talked a little bit about how do you prove the geometric series formula. This is one of the most important formulas in all of mathematics. It's extremely important to know many different ways to prove this. This is the formula for the finite geometric sum. And then you can just take the limit as k goes to infinity as long as the absolute value of r is less than 1. Okay, we talked briefly about differentiating identities. So if we know that 1 plus r squared all the way up to r to the k is 1 minus r to the k plus 1 over 1 minus r, well, if we take k equals n minus 1, we have the finite sum. It's going to be 1 minus r to the n over 1 minus r. And now if we differentiate term by term with respect to r, and then multiply by r, we don't change the powers. R to the first goes down to 1, then we multiply by r, goes to 1 times r. R squared goes to 2r, we multiply by r becomes 2r squared. R cubed goes down to 3r squared, multiply by r becomes 3r cubed. And so we get the sum of 0 times plus 1 times r plus 2 times r squared plus dot 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 plus n minus 1 r to the n minus 1 is just r times the derivative with respect to r of 1 minus r to the n over 1 minus r. And now we can just go through and figure out what this is. All right, so we would have to differentiate this term by term. Is anybody looking forward to differentiating this? What rule do you have to use? Quotient. Now, the reason we have to use the quotient is we have this finite factor, this r to the n. But if we think about what's going on, okay, yes, we have the sum of g 1/2 to the g. The fact that we have the g outside the 1/2 to the g, as we go deeper and deeper down, that g is going to get larger and larger and larger. So for instance, when g equals 1 trillion, we've got a factor of 1 trillion. Yeah, but then it's divided by 2 to the trillion. So even though the g is getting larger as we go down, as we march down, it's being multiplied by something that's so small, it doesn't really matter. So what we could do, let me see if I can copy the slide. So what we could do over here is we could say the following. You know what? Let's just study the sum. N goes from, g goes from 0 to infinity of g 1/2 to the g, and then we'll have a 2 to the n minus 1 outside. The difference between that and the sum we have to study is so small it doesn't really matter as n gets large. If n is small, like 1, 2, or 3, then it makes a difference. But when n is really large, it makes no difference. Or look at the green part that we need to use the quotient rule for. We have an r to the n over 1 minus r. When we take the derivative of this, Well, when we take the derivative of r to the n, we'll get n r to the n minus 1. When we take the derivative of the bottom, we'll have an r to the n up top. Each term is going to have at least an r to the n minus 1. Since r is equal to a half, when you take n to be huge, both factors are going to have at least a 1/2 to the n minus 1. It's going to be negligibly small relative to the first. We really don't need to worry about this. So what this is saying is that if we only care about the main term, if we wanted to, we could actually get rid of the fact that it's a finite and just extend the sum to infinity. So again, to make your life easier, it's often better to say, well, look, rather than looking at this problem, this one is going to give me the same main term. If you want the exact answer, you should use the finite one. And so now, if we look at this, when you do the algebra, you're going to get, well, what's the derivative of 1 over 1 minus r? It's going to be -1, 1 minus r to the -2, and then you get another negative from the derivative of this. So it's going to be 1 over 1 minus r to the -2. We multiply by r, so we get r over 1 minus r squared minus something. And I don't really care what that something is. Okay. What value of r we're using? We're using 1/2. So this is 1/2 over 1 minus a half. So that's 1/2 divided by 1/4. That's just 2. So this sum would just equal 2 to the n minus 1 times 2. And then the other sum was 2 to the n times n plus 1, I think. And this, of course, is just 2 to the n. Other was, I think, 2 to the n times n plus 1. And so if we looked at what we had to do, we needed the difference of the two sums. Okay, the first sum is 2 to the n times n plus 1 if n is large. The second sum is 2 to the n. So the number of gaps is approximately 2 to the n plus 1 minus 2 to the n, I think, which is n times 2 to the n, to first order. Okay. We could put in low order terms if we wanted to, but this will be the main term of what's going on. Any questions about this? So there's a lot of good mathematics in this, right? We have the geometric series, we have the finite geometric series, we have the infinite geometric series. We have take a finite sum and approximate it by an infinite sum because the infinite sum is easier to work with. We have this idea of differentiating identities. There's a tremendous amount of great stuff we see from this. That said, the calculation is a bit long and involved. There's a backdoor approach that allows us to get the number of gaps without doing any of this analysis. And so one of the things I learned when I was an undergraduate is the value of seeing the long, painful calculation first. It then makes you appreciate a lot more the alternative perspective. And this is one of the things you really want to emphasize when you're writing, that a lot of problems can be done by painful brute force analysis. It's inelegant, it'll slosh it through. Have I ever talked to you about Morley's theorem? So this is one of the lessons I learned the hard way in life. Just move this out of the way. So as you probably realized by now, I'm a smartass. So take any triangle. Whoops, I don't know how that happened. Take any triangle, and each side you can trisect the angle. Now you can't do this with a straight edge and compass, but theoretically you can trisect. Okay, and then so this will hit over here. And then when you trisect, for each side of the triangle, look at the two trisecting lines that are closest to it, and that will give you a point of intersection. So we get 3 points of intersection. Anybody want to make a conjecture? Nope.
It's a similar triangle.
Nope.
The right triangle.
Nope. You're getting closer though. It's an equilateral triangle. So Morley's theorem is you always get an equilateral triangle. I believe I hold the record for the longest proof. My proof's around 50 pages. So I made a bet first year in graduate school with two of my colleagues. We were walking into the department and somebody mentioned this result that the Greeks knew about it but did not have a proof. And I said, it's trivial. And they go, it is? Well, sure. Without loss of generality, you can make one vertex 0, 0, one vertex 1, 0. And then you just write down the equation of the points, calculate the squares of the lengths, and show that they're equal. So my friend bet me, not that I couldn't, but that I wouldn't have the patience to finish this before we got our PhDs. So if I do it, he owes me dinner not to exceed $12.50. If I feel I owe him ice cream not to exceed $2.50. This was back in the 90s when you could get a reasonable dinner and a reasonable size ice cream for stuff like that. It took me a little bit over a year to do this. I was allowed to use programs like Mathematica to manipulate algebra. The best variables to use was like the tangent of 1/3 of the angles. And if you just keep writing everything down, you can eventually get equations for the three lengths as polynomials of degree like 48 or something like that by constantly clearing denominators. And so I have three polynomials of degree like 48. And you just subtract in pairs and you show that it's equal to 0. So they must be the same polynomials. So they must be the same length. Completely inelegant. This is a brute force proof. At the end of the day, I know that Morley's theorem is true, so that's an advantage. It's a success. But I have no idea why. It's the result of a large amount of algebra. It's not illuminating. It's what is the source of the miracle? The best proof I know is by John Conway. And what he does is he does this in less than a page. He starts with an equilateral triangle and reverse engineers to get the original triangle you start with. It's a much more illuminating proof. So when you're writing things up, yes?
So that's adding lines at equivalent angles to theta.
So for here, these three angles are the same. Then these two angles are the same. And then these three angles here are the same.
So if you're just starting with these points, are you going to be adding?
You're gonna be constructing these red lines and then to the black lines, yes. It's a reverse construction process where you know the triangle you want to end up with, so you start constructing backwards to get it. So when you're writing things up, it's possible to solve things by just doing a tremendous amount of algebra. We don't want to do that if we can avoid it. We want to talk about what is the source of the miracle? Why do things work? And so we just said, look, from a discussion perspective, this is a very straightforward way to calculate what is the probability of having a gap of a given length. We just calculate how many gaps there are of length G, we find how many gaps there are total, and we look at the difference. And so when we go back to earlier, we had our formula for the number of gaps of length G, and then we can just divide that by the total number of gaps. Let's talk about another way to calculate the number of gaps. So this is the faster way to find the number of gaps. So we have our numbers m in the interval 2 to the n, 2 to the n plus 1. So we have the sums 2 to the n, 2 to the n minus 1, 2 to the n minus 2, 2 squared, 2 to the first, 2 to the 0. We have to have 2 to the n, right? Everybody agree? Because we're in the interval 2 to the n, 2 to the n plus 1. What about 2 to the n minus 1? Do we have to have that summoned? No. So that would be an epsilon n minus 1. That could be 1 or 0. What about 2 to the n minus 2? Do we have to have that? Or is that also free? Well, if I give you a number m in the interval 2 to the n, 2 to the n plus 1, do I have to have 2 to the n in my binary decomposition of my number? Yeah, otherwise it's not in the interval 2 to the n, 2 to the n plus 1. Do I have to have 2 to the n minus 1 in my binary decomposition? Do I have to have 2 to the n minus 1? Or is it possible to have it or not have it? So you're saying that any number between 2 to the n and 2 to the n plus 1 has to have 2 to the n minus 1 in its binary decomposition. It's completely free. Doesn't have to have it. For example, I could look at the numbers 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Did I get everything? Yes. These would be the 4 numbers that would have to start off with 2 squared. How many numbers? So these are, 2 squared, 2 to the first, 2 to the 0. How many numbers would there be if I had 2 cubed as my largest? There'd be 8. So it's 1, 1, 1, 1, 1, 1, 1, 1. I have to have 1 everywhere. And I could have all zeros. I could have 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1. The only one you have to have is the first one. And so everything else is free. So each epsilon k is freely in 0, 1. So how many possibilities do we have? Why 2 to the n minus 1? 2 to the n, we start counting at 0. So we have 2 to the n possibilities. If you have k epsilons that are 1, the number of gaps is what? So if we have over here, let's say we have 3 numbers that are 1. How many gaps do we have? I'm sorry? So for instance, if we have 1, 1, 0, 1, how many gaps do we have between indices? I'm sorry?
Would it just be? Oh, would it be 2 gaps?
It would be 2 gaps. The gap from 2 to the 0 to 2 squared, and the gap from 2 squared to 2 cubed. If I have 1, 1, 1, 0, how many gaps do I have? Why 3? Nope, I don't have a summed at 2 to the 0. I would just have 2. What if I have 1, 0, 1, 1? How many gaps do I have? Yeah, 2. So if I have 3 summons, I always have 2 gaps. The gap from the first summon to the second, the gap from the second to the third. So if I have k epsilons that are 1, how many gaps do I have? I have k minus 1 gaps. Okay. So does everyone agree that if I have k epsilons that are 1, there'll be k minus 1 gaps? But we have to remember, one of the epsilons is always going to be 1. Okay? Which one is always going to be 1? 2 to the n. So now, look at all m in 2 to the n plus 1, with, of course, epsilon n equals 1, and exactly k in n minus 1 of the epsilons equal to 1. So we look at all of the m's that have exactly k ones among the indices from 0, 1, 2, all the way up to n minus 1. So if I have exactly k of the indices from 0 to n minus 1 that are 1, how many indices in total are 1? Have k plus 1 indices that are 1, so we have k gaps. How many numbers are there between 2 to the n and 2 to the n plus 1 that have 2 to the n as a summand and have exactly k ones among the indices from 0 to n minus 1? So let's think about what we're doing. We have our boxes. Here's the box 2 to the n, 2 to the n minus 1, 2 to the n minus 2, 2 squared, 2 to the first, 2 to the 0. We have to have a 1 here. And then over here, we have n boxes, exactly k are 1. How many ways can we choose k of these boxes to be 1 and choose k? When I phrase it like this, is it more clear what the answer is than the first way I phrased it? It's the same problem. So much of math is recognizing that we've seen this before. If I want to have exactly k of them equal to 1, well, I've got n boxes. I'm choosing k of them to put in a 1s. So there are n choose k ways to do this. Right? And this will give me exactly k gaps. So if I want to count the total number of gaps, so here's the value of, here's my value of k and the number of ways. So when k equals 0, how many gaps are there going to be? No gaps, because I only then have the index 2 to the n. I have nothing else, so there'll be no gaps. How many ways can that happen? It's just going to be n choose 0, which is n. If k equals 1, I choose one index from the first n from 0 to n minus 1. How many ways can I do that? N choose 1. And there's only going to be one gap that's generated. When k equals 2, there's n choose 2 ways of doing this. All the way down to I could choose everything. And there's just going to be one way of doing that, n choose n. So the total number of gaps is just the sum, k goes from 0 to n, of k, n choose k. So we just have to figure out what is that sum. So any thoughts? We've now reduced the problem to counting the total number of gaps to just understanding this. Okay.
So you're saying that that is equivalent to.
This is equivalent to summing our gap formula for how many gaps there are of length g.
So is this equivalent to n times 2 to the n?
So not necessarily, because when we did the n2 to the n, we were ignoring lower order terms. Right? Remember, we threw away lower order terms. It turns out that this will actually equal that, but it only has to equal up to the main term. So the analysis we did before, we said we don't really care about the lower order terms. It turns out I think everything canceled out, and we actually got the exact right answer. But that was not necessarily true. But this is an alternative way of counting. Is we know how many gaps there are if you have exactly k summons, this k minus 1 gaps. We know you always have to have the summoned or the index of 2 to the n. So you have between 0 and n possible spots where you could choose to have the index. And so we just, for each number of indices that we choose to have, if we choose to have 6 in addition to the first one, that will give us 6 gaps. If we choose 3, that will give us 3 gaps. And so we just have to calculate the sum of k and choose k. So does now reduce it to just what is the sum k goes from 0 n of k into k. Anybody have any thoughts as to how we could do this? So what do you know about n choose k? Yes, we could try to say it equals the sum, k goes from 0 to n, of k n factorial over k minus 1 factorial n minus k factorial. Why do you think I'm writing it like that? So I can cancel out the k's. But when I do that, if k equals 0, things could be a little bit bad. But what happens if k equals 0? It's just 0. So why not just start my sum at 1? Right? So I can cancel out the k's now. Do I want to have an n? Do I want to have k minus 1 times n minus k? What do I want to have? Well, I mean, this looks close to a binomial coefficient, right? What's preventing it from being a binomial coefficient? Well, now we have k goes from 1 to n. So this would be the same. Let's let L equal k minus 1. So k is equal to L plus 1. K goes from 1 to n. So what does L go from? 0 to n minus 1. So L goes from 0 to n minus 1. And then I'm still going to have an n factorial upstairs. And then I'll have an L factorial. And what's n minus k going to be? So it's going to be n plus 1 minus L. Is that it? Or is it going to be n minus 1? So k is equal to L plus 1. So n minus k is n minus quantity L plus 1. So it's n minus 1 minus L. Gee, does that look like something in the numerator? We have n factorial over L factorial n minus 1 minus L factorial. Does this look like a binomial coefficient? What do I need to do to make this a binomial coefficient? Right, I mean, but I have the -1 in the downstairs. So is there any way to adjust the numerator, the n factorial? How could I write the n factorial? I'm sorry? It's n times n minus 1 factorial. So I'll write this as the sum, L goes from 0 to n minus 1, n times n minus 1 factorial over L factorial n minus 1 minus L factorial. And now, what can you tell me about this quantity over here? N minus 1 choose L. So this is now the sum. L goes from 0 to n minus 1. I can pull out the n, and it's just going to be n minus 1 choose L. And so that's going to just be n times 1 plus 1 to the n minus 1. Right? By the binomial theorem. And so that's going to just be n times 2 to the n minus 1. So I'm wondering, I look like I might be off by a factor of 2 from what we did before. So I might have made a small algebra mistake somewhere, which easily possible when this is being done at the board in terms of just dropping something. But fundamentally, this is how you should be able to do this. I'm a little concerned that, have we made an algebra mistake?
Why can't it be correct? Exactly what's changing in the C form.
So I'm actually expecting that this should have been n times 2 to the n. So let's calculate this another way. The more ways you can do something, the better. So let's just do it one more way, and then we'll have 3 answers, and hopefully 2 out of 3 will be the same. Right? Who has seen the movie Minority Report or read the book or the short story? So we'll study the sum k goes from 0 to n of k and choose k. So let's let f of p comma f sub n of p will be the sum k goes from 0 to n of k and choose k, p to the k, q to the n minus k. Okay. If we think of p and q as related with, p plus q equals 1, with q the complementary probability, p is the probability something happens, q is the probability it doesn't happen. This would be the probability you have k successes in n tosses. So what we can do is we can take the derivative of both sides with respect to p and then multiply by p. And so if I take the derivative, it's a finite sum, so I can move the derivative inside. Oh, sorry. I don't want a k here, no k here, just this. And what does this expression equal here? How does that simplify? What's the sum of n choose k, p to the k, q to the n minus k? What does that equal? You got to know this, guys. This is the binomial theorem. This is just p plus q to the n. So if I take the derivative with respect to p, I get a k, p to the k minus 1, but then I'm multiplying by p, so the power stays as p to the k. Q to the n minus k. And if I take the derivative of the right-hand side, I'll get n p plus q to the n minus 1. And then what's the derivative of p plus q with respect to p? It's just 1. Now, set p equals q equals 1, and we'll get the sum k equals 0 to n of k, and choose k, is just equal to n times 2 to the n minus 1. So we use differentiating identities again. So differentiating identities is an absolutely wonderful technique. And it allowed us to check and see that it is n times 2 to the n minus 1. So the calculation we did a moment ago here, this was correct. One of the big things that you need to really think about is how do you attack a problem? This is one of the only classes I think you will take in your entire career where we can be this slow and this methodical about discussing what we're doing. We're not in a race to see how much material can we cover. That's not the goal of this class. We are in a very luxurious situation where we can actually take a lot of time, talk about multiple ways to prove things, and what's the advantage, what's the disadvantage, how can you do this, how can you get to the point where you can do this on your own. It's much easier when you have a professor at the board who's been doing this longer than you've been alive.
Part on the next slide.
Yes.
Are we keeping the condition that q is 1 minus?
No, because if we had q as 1 minus p, then when we differentiate with respect to p, we would have some issue with Q. So really, I should be writing, a full derivative here because I'm viewing Q as fixed at this point. And so this would be true because Q is fixed. So I'm taking a full derivative. And then this expression is true for all values of Q. So I'm going to then set P equal Q equal to 1 to get something that's useful to myself. So the question is, which approach is easier? I love differentiating identities. This is a really nice, straightforward way to attack things. This isn't so bad. And the more of these problems you do, the easier it becomes. The goal is always to try to get to something you recognize. We know the binomial theorem. I want to get binomial coefficients. So when I have a k times n choose k, the k in the numerator is screaming to be canceled with something down below. And so that's why I'm going to get the k factorial down below. I'm going to write it as k times k minus 1. Now that I have the k minus 1, I see that it's almost a binomial coefficient. I have n factorial, I have L factorial n minus 1 minus L factorial. So it's looking like it should be a binomial coefficient with n minus 1 upstairs, not n. And then that suggests that I should write the n factorial as n times n minus 1 factorial. And when I do that, I can then pull out the n. I now have a sum of binomial coefficients, and I know how to handle a sum of binomial coefficients. Okay, so we will quickly see if we can find where have we made a mistake. So over here, we had, let's see, we had 2 to the n, n plus 1. Let me see. Okay, so we have 2 to the n times n. Okay, did we make a mistake anywhere here? G is going from 0 to n minus 1.
In the line above the green line.
Yes.
2 to the n minus 1 and plus 1 and what from there, how do we?
Well, the denominator is going to be 1/2, so that's going to come upstairs and give us an extra factor of 2. So that main piece is going to be 2 to the n times n. And then the next piece, we have 2 to the n minus 1, the sum of g. So let's see what we did over here. 2 to the n minus 1 sum of g. And we claim that that's going to just be 2. And so that's going to cancel the plus 1. So somehow we have missed a factor of 2 somewhere. So this is actually good to have a mistake like this. This illustrates the advantage of having multiple ways of looking at problems. So the question is, of course, have we somehow slipped and done a slightly different problem the second time in terms of looking at the number of summons? Is that why there's a factor of 2 difference? I don't think so. There's got to be something simple where we've dropped a factor of 2. And so when you're lecturing, it's not a huge deal. When you're writing up a book or a chapter, then it's important and you have to make sure that you get it right. And that's where I'm glad that I'm not the one who's writing this up. So go through it very slowly. The other thing, of course, is you can do some numerical simulations, write some code. Years ago, when I was teaching probability, someone had the wrong answer for a problem. She got 6, I got 5. And I knew I was right, not because I was the professor, but because I wrote code and did it, a million, a billion times, and it came up to, 5.0. So I knew I was right. But I told her, I can't find your mistake. So, if you come to my office to discuss this with me, I will give you almost full credit because whatever you've done, it's so subtle, I'm not detecting it. And it took a while for us to find what was the really small, subtle things she had done as to why we differed by 1 in terms of our calculations, in terms of what we were looking at. So you've got to be sometimes careful in terms of what intervals are you looking at and stuff like that. In terms of what we're dividing by, in terms of how many things are free and whatnot. But there's a lot of really good mathematical ideas lurking in these calculations. And so this is looking at binary where things are very nice. It's either 1 or 0. Everything is independent of everything else. For the Fibonacci numbers, the gaps are more interesting. Because if I know that an index is chosen, what do I know about the index before and the index after? in the Zeckendorf decomposition. They're not chosen. So you have a more interesting combinatorial problem. How many ways can you choose, if you want to have exactly k summons, such that you can't have two things next to each other? And then there's a whole slew of related problems you can look at. You could look at, I can have two things next to each other, but not three. Or you can have some more interesting things. I can have no more than 2 out of every 3. And you can start playing interesting games like that and ask, what kind of decompositions, what kind of number systems will you get from this? These are generalizations of binary and decimal expansions. To calculate a lot of these, there's a lot of wonderful mathematical concepts going on. So here we have both the differentiating identities as well as the combinatorial analysis. All right, so this is a good place to stop. Have a good Thanksgiving to all. Let me see if I can find a way to stop the Zoom.